Hey guys, this is Lego Massa 99 again today, and today I want to explain to you guys how to use the latest revision of the DRCHLLC Compiler. Now I have done showcase videos in the past that just basically show the compiler in action, but I never really explained how to actually use it. So that's what this video will be today. I'll explain to you guys how to use the compiler to generate your own program binary files. Alright, so before we start, I will say that all of this information is available on the Bitbucket repository for this project. So if we go ahead and open it up here, as you can see, I have it open here. All this information basically is here already, but I want to show it to you guys today. So to access it, you would go to the repository link and then click on the wiki page, and then click on the DRCHLL Compiler version 1.5a usage manual. And that will bring this page up. And there are also a couple other manuals on there that you may be of interest, like the DRCHLL uploader usage manuals and the instruction set documentation. I just wanted to show this to you guys so that if you guys don't want to follow, if you guys just want to read it or whatever, you guys can check it out here, since all this information will be here as well. So without further ado, let's jump into it. Alright, so for this video, I will be using the latest revision of the DRCHLLC compiler as of recording, which is version 1.5 alpha. And you can get this folder straight from the Bitbucket repository download page, which will be in the description. And so the program that we're going to be using today is the core compiler program, which looks something like this. So essentially, with the core compiler program, when you launch it, it says waiting for user input. And this is where you can enter all of your parameters and arguments into the compiler to basically tell it what file you want to compile, any optimizations, if you want debug mode on, any resources that you want to give the compiler to aid in compilation, and all of those things. Alright, so to be demonstrating the features and the usage of the core compiler, I will be using the Redstone Computer Fibonacci program for showcase program. And that was coded in ARCISS, as you can see right here. This is ARCISS version 1.0 code. And if you guys want to know how to set this up or all of that, I have videos on my channel that have all of that information. So this is just a regular ARCISS file. And I will be using this file to demonstrate the capabilities and usage of the compiler. Alright, so there are some flags that you can pass into the compiler, and a few of them are mandatory, while a few of them are also optional, and I will put those onto the screen right now for you guys to see. So I will explain each one of these a little more in detail, starting off with the file flag. Alright, so to show you guys what I'm talking about here, I'm going to start in by passing in the flag -f, and this will basically tell the compiler what file you want to compile. And you want to make sure that this is in quotation marks, because that's the way the compiler interprets the argument. So you're going to want to put a quotation mark, and then for me, usually instead of typing it out, I like to drag in my file. And as you can see, Windows nicely pastes the directory in there. So you need that, and then you also need the target ID. And so in this case, I want to compile for the Redstone Computer 4.0. So I would type in -t space 2 because 2 is the ID for the Redstone Computer 4.0, and 1 is the ID for the Redstone Computer 3.0 as of recording this video. So this tells the compiler that I want to compile this ARCISS file, which we've seen, which is right here. And then this is the Fibonacci sequence program. And we're telling the compiler that we want to compile it to the Redstone Computer 4.0. And now the last required flag we need is the core flag. And this flag basically tells the compiler which core you want to compile your program for. So in most cases, I like to compile it to core 1, because core 1 is usually the most stable and fastest core on the quad-core array in each of the Redstone computers. And if we go ahead and hit enter now, as you can see, it basically popped up, some things popped up on the screen, and then it went away. And if you can see here, we have now a .pb file. Now this stands for program binary, and essentially this is ARCISS's version of an executable file for the Redstone computers. And now if we edit this in Notepad++, as you can see here, it's just a bunch of ones and zeros. So what the compiler did in that split second was that it compiled this program here in ARCISS version 1.0, the language, to all of these ones and zeros, and this is specific to the Redstone Computer 4.0 on Core 1. So yeah, those are the only 3 required flags that you need to be able to compile a program using the compiler as of recording this video. And once you have this program binary file, you can pass this into the DRCHLL uploader program, which will take the ones and zeros that we've seen in here, which I can pull up again right here, the ones and zeros, into our target computer. So I conveniently have the Redstone Computer version 4.0 opened here. And yeah, so the uploader program will upload those ones and zeros into the program memory of this computer. And if done correctly, the uploader will upload it into this program space exactly, because this is Core 1's program memory space, and we told the compiler to compile for Core 1. Alright, so now I want to show you guys some other flags that this core compiler also takes in. So let's go ahead and input our required arguments first, which are the file, the target, just an example, this is the Redstone Computer 4.0, and the core. And the first of the optional flags you can add in is the debug flag, which you can enter in with -d. And what this will do is that it'll print a lot of verbose information into the console that you see here, and then we'll also write a debug log file to wherever this core compiler executable is located on your system. And this is extremely useful for when debugging this compiler, since as it mentions on the repository, and I will reiterate again, it is still a package of programs still heavily in development. So yeah, let's just go ahead and give us a spin to see what it does with when we have the -d switch on. So once we hit enter, we have already some extra verbose input of how the compiler interpreted our flags. And as you can see here, we have the source file location identified, we have the core compile target and the compile target, and then we have debug mode enabled. And now if we hit enter to begin compile, as you can see, we have a lot more information here, instead of just the compiler popping in and out of existence on the system. Yeah, and so we get a lot of little nifty information, and as you can see, we have the machine code here and also some nifty information at the end. So this program took just under a second to compile. There were 12 lines of machine code. Here's the MD5 hash, and this is useful for comparing whether compiled programs are identical or not. And then it says here that we've exported the compiled program to the desktop. You can see right here it's popped up again. And then it also tells us that it's written a debug log located at this location, and then it says press enter to continue, and that will obviously exit the compiler. And now if we go ahead and open up the location where it's written the debug file, as you can see, it's written it to wherever this core compiler file is. So if I go ahead and open this up, as you can see, we have a lot of very nifty information here. And I won't get into what all this means, because it's a lot of very technical jargon for another video. But essentially, this is extremely useful for when you have problems with the compiler and you need to file bug reports, or you need to basically show, I guess if you're in correspondence with different people about, you know, what the compiler is doing and this and that, then the debug log file is a very handy piece of diagnostic information for you to use. Alright, so the next optional flag that I want to explain to you guys with this core compiler is the optimization flag. And essentially what this does is that it allows you to enable certain optimizations that the compiler has built into it to try to optimize your code for certain circumstances. So yeah, let's go ahead and input that flag in. So first of all, we're going to go ahead and input our required arguments, which are the file, the target, and the core. And actually, I will mention you can input these flags in any order. So, excuse me, in any order. So we can just go ahead and switch these around just to show that. And let's just turn the debug flag on. Why not? Usually, since I'm the developer of the compiler, I usually have the debug flag on. And now the optimization flag is -o. And after -o, you need to provide a number of the optimizations that you want enabled. So currently, in version 1.5a alpha of the core compiler, there are 6 optimizations. And only half of them are actually enabled and implemented into the compiler. The first one is a variable clock speed optimization, and this basically allows the compiler to automatically change the speed of the target computer, so the Redstone Computer 4.0 here in this case, and also since we have it specified here, based on the instructions of the program. Now this is one of the optimizations that is not implemented in this current revision of the compiler, but it's there to mark more as a reference for future potential optimizations. The second optimization that is included here in the compiler is what's called the independent conditional branching optimization. And essentially what this does is that it splits the conditional instructions into their own line of code, because usually they are bundled together, and this potentially has massive performance gains depending on the program. The next optimization for version 1.5 alpha of the compiler is what's called redundant code removal optimization. And this is more of a collection of optimizations rather than a single optimization. And this just removes various instances of redundant code that are found in the program in this file. So if we have any sort of redundant code in here, like if we have if we type in exit twice here, it'll get rid of this duplicate exit. If we have for the redundant code removal optimization, it does remove assigning variables values of 0, because it's assumed that the RAM is reset at each compile time. So if we have duplicate lines of code and stuff, it'll clear that out, and it'll do a couple other things as well. Now the fourth optimization that you can select is what's called automatic function grouping, and this is another optimization that is currently not implemented in version 1.5 alpha of the compiler, and it's more of a note for the future. And this optimization essentially was trying to automatically consolidate repeating lines of code in a program into its own little function, and to reduce program size and increase efficiency of the program by basically consolidating lines of code down. And the fifth optimization are memory management optimizations, and essentially this enables different optimizations to increase memory performance, including the use of the cache on the Redstone Computer 4.0. So if we are aware here, the Redstone Computer 4.0 does have an 8-byte cache, which is located on each core at the top of the ALU. So this orange is the ALU, and this dark gray is the cache controller and the cache memory actually on the core. So if we go back to our compiler here, this optimization is also unfortunately not implemented in version 1.5 alpha of the compiler, but it should be implemented in future versions of the compiler as they come out. The sixth and final optimization that you can enable with the version 1.5 alpha of the compiler is what's called instruction merging optimizations. And essentially what this will do is that it will consolidate multiple generated instructions into a single instruction if it's possible. There's a bunch of checks that it performs to make sure that that's possible. And this essentially is for decreasing the program size if you want that, but in exchange it will potentially increase program runtime due to running multiple things at the same time. So you have a little bit of a trade-off that you can choose between independent conditional branching optimizations, which splits instructions, but then it's faster, or instruction merging optimizations, which consolidates instructions but makes it slower. Alright, so I've been rambling on about optimizations for a couple minutes now, but the real question still remains, how do we actually input these optimizations into the compiler here, since we still have to enter in a number? And the way to do this is actually pretty simple. So what you're going to need is some sort of binary to decimal converter here. I'll just put this on the side. I might just look this up on Google, and you can use your own binary converter or whatever. But essentially what you do is that there are 6 optimizations. So we type in 1, 2, 3, 4, 5, 6. And then for each optimization that you want enabled, you type in a 1. So for example, optimization 6, which is instruction merging optimizations, if we want to turn that on, we would change the 6th 0, since it's the 6th optimization, to a 1. And also, let's say we want the 3rd optimization turned on, we would also change this 3rd 0 to a 1. And then once we've basically changed our binary value here to represent the optimizations that we want turned on, we click convert to convert it to decimal. And then as you can see, we get a decimal value here, and this value is what you input into the compiler. So to enable optimizations 3 and 6, we would type in -O space 9. And now if we hit enter here, as we can see in the argument breakdown before the compiler starts compiling, since we have the debug flag on, As you can see here, we have optimization 3 enabled, which matches with the one that we selected, as well as optimization 6, which is this one that we've also selected. And then once we hit enter to begin the compilation, it will go ahead and compile our file just like that. Alright guys, so the final optional flag for compilation that I want to talk about is the resource flag. So essentially what this does is that this allows you to pass in a bunch of resources, as they're called, into the compiler so that you can use those resources in your compilation. Now this is synonymous to libraries and extensions and that kind of thing. And yeah, so you need this resource flag, and you need this if you're planning on using any Redstone Computer 4.0 specific code, and I will talk about more about what that means in a minute. So I'll just show you guys how to use it right now. So essentially what you want to do is that you type in your required flags first, and actually not required flags first, I'm just doing it for convention here. Put in our core and target, turn on debug mode just because I like debug mode, and then the resource flag is -r. And what you're going to want to do now is that you're going to want to pass in a resource folder in quotations, and I don't have a resource folder at the moment, so I'm just going to leave this blank. But if you don't have a resource folder, you'd probably just leave the whole flag out. Alright, so currently at the time of recording this video, the resource that you will need to program most likely is the Redstone Computer 40 extension file. So I have another program here, which is the Redstone Computer 40 GPU test program. I have another instance of it opened here, and now if we load ARCISS version 1.0 styling on this, now we have a more realistic picture of what this is. So essentially here, as you can see, what differs from our for showcase program, oh okay, never mind, it has that in there, but there is an import RC40E declaration here, and essentially this tells the compiler that we need this RC40E extension in order to run some of the code in the program. Now this is not true for this program here. This is just, I don't know why this is here honestly, since there's no Redstone Computer 4.0 specific code that this needs, so this is a redundant import. But here this is a necessary import because we have a bunch of GPU instructions, and as we know, there is only a GPU on the Redstone Computer 4.0, and it is right over here, as we've seen in the showcase video of the computer. So you're going to need a resource folder to be able to compile this program correctly. And to do that, essentially, so I created a resource folder here, and what you need for that is what's called a DRCHLLC enabler file, and you can just create this if you want. It's just based on the name that enables the internal extension. So this is one of the most realistic uses for the resources folder at time of recording this video, because there is no formal function support yet in version 1.0 of the ARCISS language or version 1.5 alpha of the compiler. Now this was one of those things where it's just basically a placeholder for the future. So let's get back to going ahead and inputting this into our compiler. So we're going to go ahead and specify our file. This is the GPU program. Then we're going to go ahead and specify our core 1, Redstone Computer 4.0, and now we have this -r. Now we're going to pass in this resource folder here. And in the future, you would also have various libraries and stuff written in ARCISS in this resources folder that you would be able to use in your programs. That's the intended use of these resources. But at the moment, it's not fully implemented in the language nor the compiler. And let's not forget our debug flag so that you guys can see what's actually going on. So once we have our resources folder specified here for the compiler, and we hit enter, now as we can see, it's detected a resource folder that we've specified, which is right here, and now it's doing a resource import. Now if we hit enter to start the resource import, as you can see here, it only finds the Redstone Computer 40E enabler file, as it's called, which is this. Now basically what this does is that it enables the Redstone Computer 40 extension within the core compiler here, and now we'll be able to successfully compile this code that has all of these GPU references in it, because this extension, this internal extension, all of the extension files are internalized because it's part of the includes supported features for native computer targets. Now it's been enabled and included in our compilation. So now if we hit compile to hit enter, as you can see, it has generated 7 lines of machine code in about less than half a second. And as you can see, we have our compiled program binary file here. Now that's only possible if we have our resource folder and our Redstone Computer 40 extension loaded into the compiler, because if it's not, the compiler will not know what those references mean in that file, much like modern compilers of this day. Alright, so that was a comprehensive overview of how to use the compiler, and I've gone over every single flag and how they work and all that stuff. So now hopefully you guys will be more prepared to and equipped to write programs in ARCISS and to ultimately upload them and run them on these Redstone computers. And just to clarify again, once the compiler finishes its job, it will generate a program binary file which you pass into the DRCHLL uploader, which is right here. This is version 1.0 of the uploader, as you can see here. And then you pass it into the uploader to actually transfer this program data into Minecraft. And yeah, that's all I wanted to show you guys today. So thank you for watching, and if you have any questions, please make sure to leave a comment and I will answer them hopefully to the best of my ability. And yeah, I will see you guys next time. Bye bye.